All right, this is the video for day 32. We are yet again talking about hypothesis testing. This time, the type of data set that we're working with are things like scatter plots. If we've got an association between two quantitative variables, we may be interested in, is there actually a relationship between the two? Or is the scatter plot that we're seeing, is the general trend that we're seeing just due to the sample that was taken? These hypothesis tests, just like every other one we've been talking about so far, is fundamentally asking the question, is the sample that we took evidence for some sort of trend? Sometimes we get samples that fundamentally differ from our baseline assumption, and the question that we're always asking is, was this because our baseline assumption was wrong, or is this just within the realm of reason? Okay, it's been a little while since we've talked about regression lines, so just a quick recap. The idea is that if we have two quantitative variables, let's call those x and y, and we have a collection of data points for each data point that has a pair of x and y values, if we make a scatter plot of these values, that may illustrate some sort of trend that's happening. If there is a linear relationship, one thing that we can do is find the linear regression line, or the least squares regression line. So in this case, that would look something like this, where this line has the equation y hat equals b naught plus b1x. I want to talk about notation a little bit. Up until now, we've been talking about means and proportions, both in populations and in samples. And because we're frequently going back and forth, we need to pay attention to which one is which. We need to use the proper notation so that we can signal what type of mean we're talking about. That's true in this context as well. For our inference for regression, working with these scatter plots, we're going to be largely focusing on what the slope is. So in this case, since our sample is this set of data points, B0 and B1 are both numbers talking about a sample. The question that we're asking, is there evidence of some sort of greater trend, is talking about the whole population. If for this entire population, we looked at the x and y values and found the slope of the least squares regression line, that hypothetical slope for the population, we're going to call beta 1. The trend here is that we will often use Greek letters to talk about the population, whereas we use English or Latin letters to talk about the sample. So beta 1 is the hypothetical slope of the relationship between x and y for the entire population. B1 is the slope of the line for this particular data set, for this particular sample of blue points. So if we're running a hypothesis test, if we're asking, is our sample actually evidence of a trend, then our null hypothesis is always going to be that, well, nothing is really happening. There's no actual notable trend, which in the context of a least squares regression line, of a linear regression line, that's like saying that the slope is 0. So our null hypothesis is going to be that beta 1 is 0. Certainly it's the case that for our sample, for these blue points, there is a slope, or the slope of this regression line is not 0, but our null hypothesis is that this just happens to be a fluke, and maybe if we took a different sample, we would get some other data points that would give us a different regression line. Our alternate hypothesis is typically just going to be that beta 1 is anything but 0, which is saying that, hey, there is some sort of trend happening. We're typically not saying what that trend is. All we're saying is, there is some relationship between the two. Okay, I've said a few times that the reason that we do a lot of the calculations that we actually do in this class isn't because we need to know how to actually calculate them. Computers can do almost all of these things for us. The reason that we go through the steps of learning the process for finding things like a z-score is to get a sense of where this p-value comes from. For a hypothesis test like this one, a question that we're asking is, all right, if the null hypothesis is true, if there actually is no trend, what are the odds? What's the probability that if we choose 14 points, that we get an example that looks somewhat like this. So this particular example appears to have a trend. What are the odds that this happens just due to random chance? Well, that's the p-value. I'm going to briefly go through how we would actually do these calculations by hand if we really wanted to, but we're now going to even more start to put this off onto the computers. What I don't want to do is have this just be a black box where you plug in information and it gives you a p-value and you're done. I want there to be some sense of what is happening under the hood, so I'm going to briefly go through these steps. But for the most part, we're not going to be doing any of these calculations ourselves, especially when we're working with scatter plots. This is something that R just does much better than we do. Okay, if we're actually going through the steps of calculating a p-value for something like this, the format should feel very similar. We're going to be using t-tests, so we want to calculate the t-score. And just like any t or z-score, what we're interested in is how many standard errors away from our expectation was our actual sample. So in this case, our expectation is beta 1. Our null hypothesis is typically that beta 1 equals 0. So this is going to be a 0 term more often than not. And what we want to say is how far away is the sample that we saw relative to that divided by the standard error. So the standard error in this case is going to be the ratio of the sample standard deviation of the residuals to the sample standard deviation of just the x values. So again, the residuals are the difference between each individual point that we have and its predicted value, its point on this least squares regression line. If we look at the collection of these residuals, we can find the standard deviation of that. We can also look at the collection of x values and find the standard deviation of that. As we know, finding standard deviations of a bunch of points is not something we want to do by hand, so typically this whole process is going to be pawned off on technology. One last point to make is that we're using a t-test. So once we have our t-score, we can treat this just like any other t-test. One potentially surprising piece is that our degrees of freedom is now going to be n-2. So it's important to keep in mind where these calculations come from, but for the most part, for these inference for regression questions, we're going to let R or some other technology do most of the calculations for us. We still need to pay attention to a few of the assumptions that we're making before we actually go through a hypothesis test for this. Our first assumption here is the linearity assumption. We're doing a least squares linear regression line analysis. Well, it needs to be the case that our data actually has a linear relationship. So we've talked in the past about how if we have a relationship that's not linear, we can reformat it so that it is. But for now, we're assuming that we're at that last step and we have a linear relationship. The example that I'll be using for this, we've used before. It's the data from the Old Faithful eruption timings. So our data set consists of pairs of points of how long the eruption was, as well as how long it has been since the previous eruption. And again, we've used this before, but let's take a look at what this looks like. If we make a scatter plot, we can see waiting, so the wait time, I believe in seconds, compared to the eruption time. So this data set looks maybe a little bit strange. We have this bimodalness going on, and you could argue that the lower portion maybe has a slope of a line that is different than the upper portion, or that maybe breaking this up into two pieces would be a better way of going about it. But for the most part, a linear relationship seems reasonable for relating these two values. Our second assumption is one that we've seen before. The independence assumption is just saying that each of these data points are independent of each other. Our third assumption, the equal variance assumption, is largely just saying that our data doesn't look like this. So what we have here is a situation where the variance or the spread of the y values is different for different x values. So in this case, if we just looked at data points with x values around 2500, the spread or the standard deviation of those points is different, is smaller than that for the set of points with x value around 5000. We can see that this spread is bigger than this spread. So this would be an example that violates the equal variance assumption. Equal variance is saying that there is an equal amount of variance for all of the different x values. Since we have this fan-like picture, this is a strong visual indicator that this does not meet the equal variance assumption. This faithful dataset is another example where maybe this condition isn't quite held. So the variance around the 50-second wait times looks to be a bit tighter, a bit smaller than the variance around the 80-second wait times. So when we come across something like this is when we would say, you know, maybe our conclusion isn't going to be completely accurate. Maybe something slightly strange is going to be happening with some of the probability calculations we're doing. Our last condition is the normal population assumption, and this one is really saying that the spread of our residuals should be relatively normal. One easy way to check this is to make a histogram of the residuals. So if we run hist of the residuals of my model, then we get this histogram. And I would say that this certainly looks at least nearly normal, so this would pass the normal population assumption. Okay, so then lastly, we want to actually do this mechanics. For the most part, we're going to let a computer do it for us. For example, if we have our linear model, we can just run summary of that linear model. So this gives us information about the residuals, as well as information about the least squares regression line itself. We've seen this grid before. In the past, we've focused on what the actual values are for things like the y-intercept and the slope. So this last column over here tells us the p-value for our null hypothesis. Remember, our null hypothesis said that there was no relationship between wait time and eruption length. This p-value is saying that even if there is no actual relationship between wait time and eruption length, if we were to go and take a sample of 272 eruptions, then while we might still get a sample that is as convincingly linear as what we saw, the probability of that happening is incredibly small. Therefore, instead, it's probably the case that there actually is some sort of trend. So in this case, we reject the null hypothesis and say that we do in fact think that there is a relationship between the two. The one last point I want to make is that this p-value is different than our r-squared value. R-squared is talking about how tightly fit to a line a certain distribution is, which is not the same as some measure of how likely it is that there is some relationship. For example, if we had a very small sample size, we could have an extremely high r-squared value, an extremely tightly packed linear relationship, but still not be all that confident about the fact that there is a relationship at all. Conversely, if we have a lot of points that follow a general trend, then we can be fairly certain that there is a trend, but still have a relatively low r-squared value. Okay, hopefully this, for the most part, is starting to feel familiar. We are still doing hypothesis testing. The only difference is the form in which our data take.